Bike frame analysis by Rist and Miranda, Whah. The CAD model on the left was created using ANSYS line models with dimensions based on the sketch on the right. The letters on the CAD model link each tube to a set of tube measurements on the next two slides. For the first geometry, we use the following outer and inner radii for each tube. For the second geometry, we use the following outer and inner radii for each tube. We analyzed the frame using two different materials, Reynolds 953 steel, a common bike frame steel, and aluminum alloy. 5 loading scenarios were tested: a friend riding on the handlebars, front tire hitting a bump, a hard landing off of a jump, a frontal collision with a vehicle, and a lateral collision with a bicycle. The following slides will show the results of the loading scenarios on both geometries, made of Reynolds 953 steel. For the first scenario, the back two vertices and the front lower vertex were fixed, with a fixed rotation for the fork tube. A total force of 950 newtons was distributed between the seat and the pedal tube. A force with coordinates negative 176.3, negative 57.29, and 0 newtons represents the proportion of the handlebar rider's weight that is supported by the fork tube. In order to simulate a front tire bump impact, the back two vertices were fixed, tube B was fixed in the Y direction, the same rider force was applied, and an 800 Newton force was applied to the fork tube, representing the moment generated by the fork upon impact. Scenario 3 looked at what would happen when the bike endures a hard landing on both wheels off of a jump. The following images show these results for both geometries. Scenario 4 simulated a frontal collision with a vehicle. In order to do so, a force of 1,000 newtons was applied at the top vertex of the fork tube, and a force of 5,000 newtons was applied at the bottom vertex of the tube to represent the moment generated by the fork. Scenario 5 looked at what would happen during a lateral collision with another cyclist. In order to do so, a force of 1,250 newtons was applied in the negative x direction at both vertices of tube B. Now to look at the same loading scenarios, but with both geometries made out of aluminum alloy. The first scenario yielded a larger deformation for the aluminum frame for both geometries, in comparison with the steel frame. For scenario 2, the aluminum frame had a larger deformation than the steel for both geometries. For the third scenario, the aluminum had a larger deformation for both geometries compared to the steel frame. For scenario 4, the aluminum had a much larger deformation for both geometries compared to the steel frame. Scenario 5 yielded much of the same results, as the deformation for the aluminum was much larger than that of the steel frame under the same loading. For buckling analysis, we looked into scenario 4, a frontal collision with a vehicle, for both materials using the second geometry. The results of the steel frame are shown tabulated below, with an image of the first mode shape. The results of the aluminum frame are shown tabulated below, with an image of the first mode shape. Critical joint analysis was done using the fourth scenario, and analyzed using both materials in the second geometry configuration. The joint in question was the bottom connection joint of the fork tube. This concludes our report.